module structures.
Okay, thanks, JD, and thanks for having me, and thank people to come. And right, can people hear me okay? Good. So all the thing I'm talking about today is joint work with Prasid, Bhattacharya, and BERT-EU. Let's start with the introduction of standard algebra. And we know that if we start with the cohomology with F2 coefficients, and that will always be the case, prime P is 2. And then we have the cohomology operations. And if we collect all of them, they form the mod 2 standard algebra. Which we will denote A. Well, then we can also say that, well, given a spectrum X, then the cohomology of that, it is the standard algebra acts on the cohomology, so it has an A module structure. So then it leads up to the question that if we start with an algebraic thing, and we can ask, well, is this going to be some isomorphism for some spectrum X? So that is the realization question. I mentioned that because, okay, so terminology is if this isomorphism happens, then we say that X is a realization of that. So it is more convenient for us to start with smaller standard algebra, namely it is generated by only square 1 or square 2, and talk about a realization of subalgebra A of 1. And well, I think I will introduce some notation first before I write anything down. So I'm gonna denote S mod 2 as the cofiber of multiplication by 2 between the sphere spectrum and also for the Hopf map eta. And I want 1 suspension. And then, well, we can cook up another small spectrum Y that is mashing those two together. So if we move to cohomology, we can sort of draw the cell diagram of them. And by that, I mean, if you consider the cohomology of S mod 2, it is going to have 2 class, and there is an action from the bottom class hitting the top class. I'll make a stick, and this action is given by square 1. So in other words, we can say 2 is detected by square 1. And similarly, eta is detected by square 2. So then I'll have a longer thing, and I'll use the blue curve indicating there's action of square 2. So we can draw the cell diagram of Y, and that will be a square that has shorter edge to be square 1 and the longer edge to be square 2. Right. So classically, this story is majorly developed by Adams and Davis Mahowald. And well, what they did is more than that. They also make connections with V1 periodicity. And right, so we know that if we have a self-map between, wrong color, okay. If we have a self-map of like smaller complex, let's say X, let's just call it V. Right, then we can produce a very nice family of the stable homotopy of spheres by just doing the composition. By doing the composition of embed the top cell, and then you snug the self-map in between. And then projects down to the bottom cell. So, right, and there is a famous family of V1 that matches up with the image of J. And I'm just gonna briefly talk about something Davis and Mahowald did in their paper that is relevant to the talk to make a base storyline. All right, so first, there is V1 to the 4th self-map on S-mod2, and this is Adams constructed using the total bracket argument. So that is already very nice, and well, but there is a tendency that it makes the periodicity, so this index, lower as possible. Because if we have a lower periodicity, then we get more freedom when we construct this family. So, and Davis Mahowald find the V1 self-map on the spectrum Y, and that is of periodicity 1. So, and how they do it is they first construct a spectrum A1. So they first construct a small spectrum A1, and they use the standard real projective space. So yeah, recently I'm coming back to learn about that because I think it's relevant to the root invariant seminar. And I wonder if there is a motivic analog of that, but yeah. So they take the cofiber of the map from, I think the truncation number is this, to construct A of 1, and they realize that the map Y mapping into that gives a surjection in the cohomology, and the cofiber of J is the 3 suspension of Y. And they also did a small computation via the atom spectral sequence to show that, okay, so this, if you go one step further to this co-fiber, and then you have this shifted self-map on Y, and that matches up with one class from the two suspension to Y, and that's how they identify the co-fiber of this V1 self-map with A1. All right, so so back to the realization problem. First, let me just draw what A1 looks like. So A1 is A of 1, sorry, there's two A1s, and one is the spectrum and one is the algebra thing. So A of 1 is the standard subalgebra generated by square 1 and square 2. And it has 8 class. And there are square 2 actions. Right, and right. So this is what I'm drawing is only an A1 module so far, because there are square 4 actions that I'm not taking considered yet. So Davis and Mahowald have a theorem that I will write down here. So they find out there are 8 V1 self-maps whose co-fiber is A1. So I'm probably abuse notation to use A1 to be like indicating that only the A1 module structure of the spectrum that has 4 distinct homotopy types. And then such that it is a realization of A of 1, and it matches up with the 4 A module structure of A of 1. And let me just talk about the 4 A module structures on A of 1. So you're guaranteed to have one square 4 action from the second cell hitting the fifth cell. And this is given by the Adam relation where 4 square 1 is the same as square 2 square 1 square 2. And there are optional ones. I'm just gonna copy this thing. All right, so there's optional square 4 from the base class hitting the 4th cell. And there's also optional one from the second cell hitting the 12th cell. Okay, and you have the one with only that, or you can have each of them separately. Right, so I should also mention, if you consider the spanner wet-head dual, those two are dual to each other. And the one with only one optional square force, they are self-dual. All right, so maybe it's good to do a little summary of their works that we're going to use as a base storyline. So first, they construct the spectrum A1. That is realizing the standard subalgebra, sorry. So far is as an A1 module. And then they find a V1 self-map between Y. Using some computation tool, and they identify the cohomology of the cofiber with the spectrum they constructed. And then they analyze the A module structure of A1, and that is the same as analyze the homotopy types of A1 classically. But algebra thing is easier to put hands on, so I think starting with A module structure on the algebra things is handy. Yeah. And then they connect the story, this A module structure with V1 self-maps. Namely, they did figure out like all the 8 self-maps, and 2 of them matches with one module structure. So they figure out the connection. So yeah, what is I think I should put down which V1 self-map cofiber is a realization to which A module structure, or let's say given an A module structure, it is realized by which V1 self-maps cofiber. All right, so that is our storyline, and we are trying to answer those questions in the R-Motivic homotopy theory setting, and I think this is a good time to pause for questions. All right, great. We'll have the picture in the next page. Anyway, so for motivic cohomology theory, and it is introduced by Vygotsky, and I need to be careful, I always spell the name wrong. So Vygotsky gives the notion of motivic homotopy theory over a field where you start with the algebraic covariety over the field and consider the simplicial sheaf, and then do some gadget to make the affine line to be contractible. Of course, that's a very coarse description, but I'm not gonna turn into the details of the construction. So a couple of things that are worth mentioning is, so if you start with a variety, that's gonna give you something there, and because of the simplicial structure, the spheres are bigraded. Okay. So there's one family of sphere that is S1, 0, and that is the boundary of the simplicial one, and we call it simplicial sphere. And there's also the geometric sphere that is the GM, that notation, right? So it's parallel to like punctured plane. Okay, so so there's also the notion of Eilenberg-McLean spectrum and the spheroid algebra there. So let me just give more notation. That is SH, and I'm gonna put an upper script R to indicate that's the R motivic one. And you do have this functor that is called Betty realization to map it to the C2 equivariant stable homotopy category. And then you have the functor that is forgetful, or we call it restriction, send it back to classical. Right, so since we have the notion of standard algebra on R motivic, but we need to be a little bit careful. So I'll put a superscript R to indicate that the R motivic standard algebra, but it is actually not an algebra. It is a co-algebroid in the sense that the multiplication is not commutative, so it's not very well behaved as classical. Taking complex points, composite. Yes, I think that's true, and right, that is like involving with another corner that I'm not drawing in the picture. That is the C motivic, stable homotopy group, and then the square commute. Yeah. All right, so let's talk about the multiplication by 2 map that we have in classical. So we can pull it back along those functors such that they land in R motivic and consider them as a lift. And it turns out that multiplication by 2 has 2 lifts. And one is the boring one, and by boring, I mean if you stop in the middle, it doesn't have any action. So it has trivial actions. And let me try to stuck one page in the middle. And then there's another one that we use the notation as H. So this H is 1 minus epsilon, where this epsilon is the twist map switching between two copy of 1 sphere. So why this H is important is because it is the R-motivic Hopf map, and by that I didn't mean it to be connected with eta. I mean the degree 0 map of the Hopf invariant problem 1 in classical. Right, so what about the real Hopf map eta? Well, sure, it also has 2 lists. And one is the boring one, and because the boring one doesn't have the motivic weight to like place in the right place, so we just abandon that. And we also have this one has action, and this is motivic eta, and it is also the half construction of the 1-1 multiplication, multiplication on 1-1 speed. All right, so now let's take a look at how the coefficients are different from classical and add up the complexity. Right, so here is a picture of the coefficients, and by coefficients I mean the cohomology over a point. So this we also denote that as M fold M2, and it is isomorphic to F2 adjoint 2 generators, tau and rho, where tau is cohomology class in the degree 0, 1, and the rho is also in homotopy, and it is the map S0 to S sigma, right, in C2S variant. So from the picture, this picture, there's only square 1 and square 2 drawing in, and you can see there's action square 1 on tau, that is rho. There's also square 2 on the like tau multiples, like tau square, but you don't need to memorize all the information there, because the Cartan formula in the standard algebra is going to give you that information. So the thing is, capture the information, the actions on the generator is enough. All right, so we did use a different approach than Davis and Moholt in classical. So we construct this A1R using a different approach. That is a method of Smith. That is well stated in Ravenel's Orange Book, Appendix C. So briefly speaking, it is the way to construct new spectra from idempotents acting on smaller ones. And then we choose a complex Q, that is a question mark, because the composition of H and eta are 0. And then we can, we find one idempotent using the like Young tableau, and then identify this idempotence acting on 3 copy of that is 3 A1 module. Right. So and then we did the computation from the sorry, it's harder for me to say things and write things at the same time. So we compute this V1 self-map of Y in the X over this Y smash dual of Y using the atom spectral sequence. So that is gonna give us a class in the self-map, briefly speaking. And then we identify the cohomology of the cofiber with the A1 we find. Right, so this step is exactly the same as Davis and Mahold. Well, I should make a warning that even though we identify their cohomology, we do not know that if the cofiber itself has the same homotopy type as the A of 1 we constructed, though. All right, so maybe it's good for us to see smaller example of realization, and by that I mean let's take a look at A of 0 that is only generated by square 1. So this is a picture of A0 of R. And only as A0 of R module, because not the square 2s are not drawing in this picture. And you can see that classically there's only like one class 0 and class 1 connected by square 1. And motivically, they kind of expanded to be the relation between 2 cones. So there are spaces for more complicated things, namely square 2, to happen and drawing in. So yeah, so let's just look at the generator. So whether this class supports a square 2 gives 2 different A module structure. And well, previously we see there are 2 lifts of multiplication by 2 in classical, namely if you send it back, it is multiplication by 2 in classical. And they are multiplication by 2, that's the Boring map, and multiplication by H, the Hopf map. And it turns out these are the 2 realizations of A of 0R. And right, so you may wonder why 2 that supports a square 2 and heating the like rho times the second generator and H doesn't. And there is interesting interpretation in terms of the geometry fixed point. So oh oops. Right. So let's back to, well, I don't know back to where. Yeah, here there's besides the restriction functor here, there's also the geometry fixed point functor. I'm just gonna write again. Going back is a bit annoying, which we denote phi. And what it does on coefficient is its inverting row. So roughly speaking, is reducing every diagonal line to one class. So that is to say, if I apply that to the Edinburgh-MacLane spectrum, I'm using underline, that is giving us polynomials on classical. There is a wedge of suspension. And it is a fact that the geometry fixed point of 2 is 2 because it doesn't have action, but the geometry fixed point of H is empty. Right, so we also have the work to do a comparison of the geometry fixed point on the squaring operation. So roughly speaking, I think I'm using some illegal notation, but if you, no, sorry, I need to start with the geometry fixed point first. If you do an equivariant squaring operation on the equivariant cohomology class, this is equal to you cut your squares in half and reduce it to non-equivariant case. So roughly we can see that, well, this 2 class is connected by this square 2. So after applying geometry fixed point, it becomes a square 1. So that matches up with geometry fixed point of 2 is 2. And for this one, well, we don't have the square 2, so the geometry fixed point of H is empty. Right. So that's the realization question for A of 0, and there's 2 realizations of that. And come to A1, things get more complicated. And right, so here is a picture of A1 with square 2s only drawing in generators, because otherwise it will make the picture more complicated. So here are the 8 classes that if I don't want to draw the whole cone, I have a picture here with the label matching up with that, and each dot is one whole cone. Right, so here the dotted line is hitting tau multiple of that. So we have 128 different A-module structures, and it's given by these restrictions that I listed. I pre-write it because I don't trust myself and write it all right at it early. Right, so these relations basically are again using the Adam relation, and well, right. So they coming from there, and those Greek letters, they are placeholder. They can be 0 or 1, and that will determine whether 1 square 4 exists or not. And except this J24, all the things are independent of each other. So if you count, there are 7 of them, giving the 128. What is the dual? That's a great question. I think they are self-dual. Okay, they're self-dual. Because square 1 and square 2, they're antipolar themselves. Okay, so Well, we know that there are two lists of 2, and there's only one list of eta that we consider, so that give us two candidates of y. Well, one we denote y sub 2, and that is given by S mod 2 smash S mod eta. And the one is, of course, S mod H smash S mod eta. And they differ by square 4 on the bottom class. So the two ones, they have square 4 hitting the row multiple of the top cell, but square 8, the YH doesn't have that. Right, so classically, it is a self-map between the spectrum Y. There's no ambiguity about that. But armotivically, the V1 self-map, it can map between, like, it can map between Y sub 2 and Y sub H. So it's actually between the class of list of Y. So yeah, maybe it's not exactly a self map if you put it in the strict case, but yeah, we do find some connections between, like, in the sense, if you give one specific A module structure of A1, then if it's like the cofiber of self map between Y2 or YH, or mapping from one or each other. So this is our theorem. So I'm trying to draw the cofiber sequence first and try to explain things later. I'm leaving the subscript and empty on purpose for now. I think I'll just go monotone for now because that's not very important. All right, and then back to Y. So this map, the bottom dot is hitting the sum. So namely, it is hitting x31 plus y31. And our theorem says, well, let me give a subscript that is epsilon here and delta is there. So that epsilon is h if beta 2 5 plus beta 2 6 plus gamma 3 6 is 0, and if it's 2, that's 1. And delta is h if alpha 03 plus beta 03 is 0, and 2 if it's 1. So yeah, so that is to say, if you have a square 4 on this class, because that's like a y of 2, y of 2 has this square 4, that means your x31 plus y31 supporting a square 4. And that is exactly matching up with this class stat. So in other words, if this is 0, then x31 plus y31 doesn't support a square 4. So we can tell whether it has sorry, how do I put words together? If there is a square 4 on the Y mapping in between by looking at the A module structure, whether there are square 4 on A of 1. Right, so I think I'm -1 minute. Let's wrap things up with some questions. So it is the current working in progress that we show all those, we give like what which of the 128 modules they're dual to something. Yes, they're self-dual condition and such, but it is still fuzzy to write down. Right, so we have a criterion of which of these are self-dual. And right, so we also showed all of those 128 homotopy types, they are realizable. They're realizable as some R-motivic spectrum. But yeah, we do not know how many self-maps are there, and it is unclear we have that mix and match criterion. Right, so I guess spectral sequence is not a sensitive enough tool to tell the homotopy types of two spectrum, so there's still a lot more to develop there. All right, so maybe I'll stop here. Thanks.